Good morning, everyone. Today we're going to be doing section 5.3, day 1. If you would pause the video, and you can do these at the whiteboards or you can do them here at your desk. The goal is to find the interval when the original function f of x is decreasing. All right, hit pause. Okay, now when you're done, let's go over this. So what do you need to do? Well, you need to first find the critical points. Critical points are when you take the derivative, factor the derivative. So you can see the derivative has a common factor of 12x. I factored out the 12x. I set each factor equal to 0 and I solved. Those are my critical points. That's where the derivative is equal to 0. So then I have to check what is the derivative doing to the left and right of those points. I like to use a sign chart. Sign chart for me kind of tells me what the graph is doing, but notice if I'm doing the sign chart of the derivative, so here's my derivative, it's just a parabola. It's a positive parabola that's opening upwards. So if you think of just drawing that parabola is the graph of f prime. And notice anything to the left of 0 is going to be above the x-axis, so positive derivatives. Anything below, anything between 0 and 2 is going to be below the x-axis, so I'll have a negative derivative. And then anything past 2 is above. So that tells me how the derivative is changing signs. And from that, we can make our conclusion that the function f of x is decreasing because the slopes are negative between 0 and 2. So my justification, f of x is decreasing from 0 to 2 since f prime of x is less than 0. So that's the reason why. Now, since we have this on here, I could also ask you a couple other questions. Like another one was, when is the function f of x increasing? Well, it's increasing on the interval from negative infinity to 0 because the derivative is above the x-axis or positive, as well as the interval from 2 to infinity. So notice my justification, because the derivative is greater than 0, I knew when the function was increasing. And since we know when the function's increasing and decreasing, I could also make a conclusion about what's happening exactly at 0 or at 2. Well, if my graph goes from positive derivatives to negative derivatives, at x equals 0, there's a maximum of the original function because f prime of x changes signs from positive to negative. So maximum right here at the critical point of 0, which would make the critical point of 2, where we go from negative to positive, that would be a minimum. So I'd have a minimum at negative 2 since f prime of x changes signs from negative to positive. So these are 3 other things I could ask you, and the work is all the same. All right, what we're going to be doing today is we're going to look at the relationships between f prime, and f double prime. So just really quick, we have our function of f. That's where we could determine if there's absolute maxes and absolute minimums. Are there any flat spots? Are there any local max or local mins? That's what we explored last week. Well, this week we're going to extend that thinking into what happens, how do we know if a graph is curved upwards? That's called concave up. Kind of like here we're concave up, versus curving downward, so concave down. And that relates back to the second derivative. So a good thing is we're going to review a little bit of what we did last week. All right. You have a worksheet here. The sub should give you the worksheet. It's titled AP Calculus AB, Chapter 5, Applications of Derivatives, Activity, Analyzing Graphs. So your job is to look at the graph that's provided and notice, you'll actually notice it's the same graph every single time, but we're going to change what we call it. So to start, we're going to say this is the graph of f, the original function. Highlight portions of the graph of f, which is increasing. So I'm going to use a yellow highlighter for that, and then we'll do a green highlighter for decreasing. And your job is to highlight those intervals on the graph and then answer the questions. So why don't you hit pause, work through this, and we'll reveal the answers. Since this is the graph of f, so decreasing is anytime you have negative slopes. You see I have 3 intervals where I'm decreasing. Increasing is when I have positive slopes. And then notice the highlighted pink spots, those are the spots where the derivative is equal to 0. Those would be my critical points. So first question, what are the x-coordinates of the relative maximums? Where do the maximums occur? At E and H. K, excuse me, E and K. What are the x-coordinates of the relative minimums? B and H. Those are the lower spots on the graph. And then on what intervals is f increasing? That's the yellow highlighted parts from B to E and H to K. And then when are we decreasing? We are decreasing on the green spots. So we go from negative infinity all the way to B. And then we go from E to H and K to infinity. And notice these intervals are all set up by x values. All right, that brings us to the first derivative test. Suppose f is a function that is continuous on the interval I. Suppose that c is a critical number. Now, notice c is a critical number. That means its derivative is 0 at c. And suppose ab is an open interval in I containing c. What does all that mean? Well, if the derivative of f is positive from A to C, and then it goes to being negative from C to B, there's a maximum value. So notice that's the same thing as saying if my derivative goes from being positive to negative. So we would say f prime of x goes from positive to negative. Right? So if that's true, then my conclusion is there's a maximum value. Well, what if it's flipped around? What if the derivative goes from being negative on the beginning interval and then positive? So we go from decreasing slopes to increasing slopes. That's a minimum. And we did talk about that last week. So when I go from negative to positive, there's a minimum value. Now, f prime of x, if it does not have a sign change, so if it's the same sides on both sides of the interval, then it is neither a local max or a min. All right, now we're going to do the same thing on the second part of the function, but this time you're going to pretend that the graph is the graph of f prime. And I actually believe that this is the second page of your packet. Yep, so this would be page number 2. We actually didn't do the bottom part of that first page yet. We'll come back to that. All right, so go ahead and try this. We'll pause it. So this time, when we're looking at the graph of f prime, notice how I labeled the graph. We're looking on what intervals of the graph is f increasing. Well, f is increasing anytime the derivative is positive. So all the highlighted yellow intervals are whenever the derivative is greater than 0. So from negative infinity to a, remember we always read a graph from left to right, and we write our intervals involving the x coordinates. And then we go from d to g, that's this part here, and I to L. Now that's where it's increasing, but the y, that's probably the most important part. Why do I know that's true? Because the derivative is greater than 0. So now let's look at the negative values of the derivative, which is when the original function is decreasing. Those are the green intervals from a to d, f to I, and L to infinity. And then why is that true? Because the derivative is less than 0. It's below the x-axis on the graph of the derivative. So now we got to classify the x-coordinates of any relative extremas. That's max and mins. Remember what we're looking for. I always focus on the reason first. If we're looking for a maximum, that's when the derivative changes signs from positive to negative. So I go from an increasing to a decreasing slope or a positive to a negative derivative. There's a maximum at A. Same thing here at G. We have maximums. So we have a positive derivative to a negative derivative, maximum. And then here we go from positive to negative at L in the derivative. So where would relative minimums occur? Relative minimums occur when f prime changes signs from negative to positive. So here at point D, I have a negative derivative, and then I have a 0 derivative and positive. So I change signs from negative to positive at D, which means a minimum. Same thing here at I, negative to positive. So we have 2 local or relative minimums and 3 local or relative maximums. All right, the next idea is this idea of concavity. Concavity is talking about a shape that goes concave up or concave down. So concave up, think of holding water. Concave down, think of like a parabola opening downward. The water runs off. So that's the difference between concave up and concave down. So how does that relate to the function and its derivative? Well, let's see. So suppose f is a function that is continuous in a closed interval from a to b and differentiable on the open interval from a to b. F is concave up on the interval from a to b if the graph of f lies above each of the tangent lines throughout the entire interval. So if you look at that, concave up. If I draw a concave up graph, and then we look at the tangent line, the graph itself lies above any tangent line that is drawn. You can see all the tangent lines here. The original function lies above. So that's how we can define concave up. Concave down is the same general idea, but instead of the tangent lines lying above, now the graph itself is below all the tangent lines. So here we're concave down, all the tangent lines lie above, so the function itself is below the tangent lines. Definition of an inflection point. What is an inflection point? Well, an inflection point is a spot at which concavity changes. So let's say I have a graph that's concave down, and then at some point it starts to turn concave up again. So concavity changes at the point of inflection, and you can see right here we go from concave down to concave up. And that is going to be an inflection point. So what we're going to do now is going to turn to the graph of f. Now this is back on page 1, so we're going back to the front page of this, and we're going to highlight the intervals of concavity. So for concave up, let's use yellow. For concave down, let's use green. And then I'd like you to answer those questions at the bottom of page 1, and we'll go over the answers shortly. All right, so here we've got concave up is when the graph opens upwards or holds water, and that's the green or yellow highlighted piece. So we have 2 intervals of concavity where we're going concave up. Concave down is where the water would run off. And then these spots right here at C, F, and J are the spots at which we change concavities. So we change from either concave up or concave down. You can take a look here and see that at C, we go from concave up to concave down. F, we go from concave down to concave up. And I is concave up to concave down. So those are the points of inflection or inflection points. We already talked about where concave up is. That's the yellow highlighted spots. And then concave down is the green highlighted spots. That's where the graph opens downward. All right. Next page, we'll go back to page 2 now, and this is the middle of the page. We're going to look at concavity on the graph of f prime. So it's the same graph. It looks like the same thing, but now we just have to make a connection. Remember, this is being interpreted as the graph of f prime. So go ahead and answer the questions when we're concave up, concave down, and inflection points based off of the first derivative. Okay, so we're going to be looking at how to find concavity based off of the graph of the derivative. Well, to start, let's look at concave up. What has to be true when f is concave up? That means the derivative is increasing, or when does the derivative have positive slopes? So you can see the yellow highlighted areas from B to E and from H to K are when f prime of x is increasing Therefore, the original function is concave up. So when is f concave down? When the derivative is decreasing or has negative slopes, and that's from negative infinity to b, e to h, k to infinity. And then the spots at where the points of inflection occur on the original graph is when we change from concave up to concave down. Notice those are the spots where we have horizontal tangents on the graph of f prime. So that's b, e, h, and k, and that's where f prime has horizontal tangents. All right, now we're going to look at the graph of f double prime. If you flip it over to the very last page in the packet, it's the last graph. Identify the intervals where we're concave up and concave down, given that this is the graph of f double prime. So the graph of f double prime will be concave up whenever the second derivative is greater than 0, which means when is the second derivative above the x-axis? That's from negative infinity to a, d to g, and I to L, the yellow highlighted intervals. So when is f concave down? Notice how we're always making a conclusion based off of the original function f. We're concave down when the second derivative is negative, so anytime we are below the x-axis, from a to d, g to e, and g to I, and L to infinity. And then where are the points of inflection? Points of inflections will occur whenever the second derivative is equal to 0. And there's a little bit more to that we'll talk about later on, but that is at a, d, g, I, and L, because that is where it crosses the x-axis of the second derivative. All right, so how does this all relate? This is where you're going to want to pause and take notes, but what have we learned? Concave up. Concave up happens when f prime is going up and the second derivative is positive. And then concave down is when the second derivative is going down or decreasing and f double prime is negative. Points of inflection occur where concavity changes. That's where f prime of x has a max or a min. That's where the second derivative is equal to 0 and has a sign change. So it has to change from positive to negative. Or, we didn't see this one on our graphs, but the second derivative could equal 0 or it could not exist. And there could be a sign change. We'll see that in upcoming units. Feel free to pause this video and write down anything that you need to here. We're going to review some of this with what's called the second derivative test. It says, suppose f is a function for which f prime and f double prime exist on the open interval from a to b. Suppose c lies in the interval from a to b and is a critical number. So that's key. C is a critical number or a critical point, which means we know the first derivative is equal to 0. Right? That's what a critical number is. So then what do we know? If the function f double prime of c is negative, so that's saying if we're concave down at c, then c is a local maximum. Well, think about that. Let's say I have a value c here, and the second derivative is negative, so it's concave down. And because we know it's a critical value or a critical number, that means its derivative is equal to 0. Therefore, the only possible option is this has to be a maximum point. Likewise here, suppose f double prime of c is concave up, so it's greater than 0. At c, so let's just say we've got a c value here. We know it's a critical value, so we know that the first derivative is 0. And then it has to be a local minimum at c because we're concave up and the slope is 0 at c. So that's called the second derivative test. It's a pretty quick way to determine if we have maxes and mins, but it all relies on if we know that we have a critical value. or a critical point. All right, I'd like you to pause the video and try this one, and then we'll go over the answers. All right, so let's look at critical points. Where do we find critical points? This is the graph of f prime. Critical points are wherever the derivative is equal to 0. So right here and right here, -2 and 3. Find inflection points. Inflection points are when the second derivative is 0, so I'm looking for horizontal tangent lines. And I want to look for a sign change from increasing to decreasing, so I have a maximum here, which is the second derivative. I estimated this at -0.5. It might be -0.25. We're not really sure, but I just said that was an estimate. And then right here at 3, notice 3 is both a critical point and an inflection point, which is completely fine. My justification for that is we know the second derivative is 0 at those 2 points, and there's a sign change from positive to negative, or from negative to positive in f double prime. Right. Find the intervals where we are concave up. Concave up is whenever f prime is increasing, so this is the graph of f prime. We are increasing from -infinity all the way to -0.5. And we're increasing from 3 to positive infinity. And then where are we concave down? When f prime is decreasing. So we're decreasing in between the 2 points of inflection from -0.5 to 3. All right, homework tonight is in the textbook. Please make sure you give this your best attempt. Answers will be posted at some point throughout the day. You can go back and check your answers as you're doing your work. Good luck to you.